Good afternoon, everyone, and welcome to our first in-person physics colloquium of the year. I'm delighted to be able to kick off this quarter's series with introducing our speaker, Professor Feng Wang from UC-Berkeley. Just a little background on Feng. Feng graduated from Fudan University in physics, and then he completed his PhD at Columbia University in 2004. He subsequently came out to the Bay Area, first as a Miller Fellow at UC-Berkeley, and then assistant professor, associate professor, and full professor in the physics department. So Feng has been a real pioneer in using optical techniques primarily to study different nanoscale materials. He's made a lot of very significant contributions to understanding the electronic properties of carbon nanotubes. More recently, he's looked at 2D materials and 2D heterostructures. And I've always been very impressed by Feng's ability to combine a very sharp focus on an interesting physics issue with discovering the right experimental technique to address it. So I think you'll hear some of that in the talk he's going to give on some of the recent developments. So delighted to have you here, Feng.
Thank you, Tony, for the introduction and the invitation. It's really a great pleasure always to visit Stanford across the Bay. In particular, being invited by Tony. As some of you might know, I got my PhD degree actually with Tony. He converted me from a prospective theory student into an experimentalist, and have taught me everything about how to do physics research. So today I will tell you some of our recent effort trying to design kind of artificial quantum materials using Van der Waals heterostructures. Okay. Also, if you think about what condensed matter physics or solid state physics want to study, we mainly just want to understand how does the electron behave when it is put in a periodical lattice, like when you have a crystal structure. And the answer is the electron can behave in many different and interesting ways. So you can get all kinds of phases from metals to semiconductors, but more exotically like superconductors, magnetism, or even topological phases. So one key question in condensed matter physics is how do these quantum phases emerge? How do they compete with each other? And whether there are other interesting phases that we can explore. And to address this question, it would be nice, if possible, to have some designer model system that you can play with and to control the different parameters so that you can test the different theory. And I would like to tell you Van der Waals heterostructure provide one type of platform that allow us to have those kind of design opportunities. So the best known and most ancient Van der Waals material is graphite. So people actually made it into pencil and use it to write. So when you write on your paper, what you are doing is exfoliate this structure on the right, where you have these strongly bonded layers that are covalently bonded. But between the layers, they have very weak interaction. They have basically Van der Waals bonding. And when you write in the pencil, you can basically break this Van der Waals bond and you can cleave the thin layers. So a question that people start to ask is, if we can cleave this thinner and thinner, maybe we can get into a single atomic layer of this material. And indeed, people were able to achieve that. So they can actually exfoliate graphite into single layer graphene by just using Scotch tape. So what you do is you just use Scotch tape and kind of exfoliate multiple times. Then by luck, you'll get all kinds of thin layers like monolayer, bilayer, trilayer, and so on and so forth. And the discovery of this way to create atomically thin layers got a Nobel Prize more than a decade ago. So in addition to graphite, there are many different types of layered materials with this weak Van der Waals bonding, and you can exfoliate them into individual layers. So an interesting proposal then is, why don't we all put this atomically thin layer together, just like Legos, and build a Lego of this heterostructure. Also, first, it's very easy to draw a figure like this in Photoshop. A question is whether this cartoon can be realized experimentally. And indeed, research found it's possible, actually, just use rather simple, like a plastic, that you can pick up individual thin layers of this 2D material, one on top of each other. And then you can release them onto the substrate and form, indeed, this Van der Waals heterostructure. And when you take a closer look at this heterostructure, they're almost as good as shown in the cartoon. They actually have atomically clean interfaces, as shown in this TM image. To some extent, that's one of the biggest surprises of these 2D materials. Or when you just do everything in ambient condition without UHV, you are actually able to make this stack of atomically clean materials. And what happens, which very fortunately, is when you stack these 2D materials, those dirty things are not bonded strongly on this Van der Waals material. So they actually get pushed away. So as a result, after you assemble them, you can actually find the regions that are perfectly clean heterostructure. And these Van der Waals heterostructure, or once you made them, can be very interesting and very special compared with conventional materials due to several kind of important aspects. First, you can combine very different material and stack them together to create a heterostructure without the limitation of lattice matching, which is kind of a really constraint what you can do with, say, MBE growth of heterostructures. The other very interesting aspect and important aspect is these layers can be atomically thin. What that means is all the electrons are sitting on the interface. When you put two layers together, or electron in one layer will see the other layer very strongly. As a result, the heterostructure behaves very differently from isolated monolayer. So each of the heterostructure is a new quantum material that doesn't exist in nature. So, and you can see there can be a lot of different combinations that you can make once you stack two layer or multiple layer together. And another very important aspect is, because we are stacking these individual layers, we can actually contact them separately. So you can really do electrical contact and control of every individual layer in the heterostructure, which is simply not possible in conventional materials. And combining this, it gives us really unprecedented flexibility to engineer artificial quantum materials. So as you can see, there is a huge phase space. And the question, then we need to find a good question to ask. In order to find a good question, let's start with some basics of solid state physics. So we all know the fundamental theorem of solid is the Bloch theorem, which says when you put electrons in a periodical lattice, they basically will form electronic bands. So here we kind of show behavior in a 1D periodic band. So when you have free electrons, the energy is simply proportional to momentum squared divided by 2 times mass, so you have a parabolic band. Once you have a periodical potential, the electron wave function can scatter over the periodical potential, and you will form electronic band that are separated by a finite band gap. And if you look at the energy bandwidth of individual band, especially if you look at the lowest band, you can see it's roughly bounded by the kinetic energy at the boundary. So the boundary has a momentum that's roughly pi over L. So we know the bandwidth is either comparable or smaller than p squared over 2m. And it has this kind of specific scaling behavior of the periodic lattice. We all know that this formation of electronic bands really give the most important result on solid state physics, and that is how to explain metals and insulators. So when you add the electrons in these electronic bands, we know electrons are fermions, you need to add them one by one and to higher energy levels. So when you fill all the electron and you are left with a partially filled band, Wilson tells us a long time ago that should be metal. On the other hand, if you kind of fill a completed band, you get insulator. And arguably, this is the most important result in solid-state physics because it allows us to understand insulators, metals, and semiconductors, which are insulated with relatively small gap. And that, to some extent, is the foundation of all the electronics semiconductor industry. However, this picture made us assumption that is the electrons don't interact with each other. So electrons only fill all the available states. But in reality, electron has charge, and they can interact very strongly with each other. And that can break the picture in some situation. And one of the most striking example is proposed by Mott in 1949 in his Gedanken experiment. He says, if we just take a piece of metal, say lithium, which has 1 electron per lattice side. So because electron can hop between the adjacent atoms, so the electron will be delocalized and you form electronic bands. And when you have 1 electron per lattice side, that corresponds to a half-filled band because, or in principle, each atom you can have spin up and spin down electron. So 2 occupation if you neglect electron interactions. So as a result, Wilson's rule tells us lithium is half-filled and it should be a metal, which is certainly true. But Mott says, what if we can artificially change the distance between the atoms? And let's push the distance to be more and more separated. So you can see when they are very well separated, all the atoms don't talk to each other. So electron cannot hop very effectively. As a result, you have suppressed kinetic energy and you have a very flat or narrow band. So when the band is very narrow, the Coulomb interaction becomes very important. So for example, or if you neglect the hopping of the electron in a single atom, you don't want to have 2 electrons on the same atom because it will have an energy penalty of double occupancy. So as a result, Mott said, sooner or later, you are going to get an insulator, and that's known as Mott insulator at half filling. And this idea of metal to insulator transition by, or simply varying kind of the importance of electron correlation is a very important idea in physics because first, this metal insulator transition, as simple as we just showed that it must happen, but we really don't know how it happens because this metal insulator transition is extremely difficult to describe theoretically. And one way to appreciate it is, this transition does not really break any symmetry. So what you have is on one side you have a conductor. The lowest energy excitations are carried by fermions. And on the other side you have insulator where you have low energy excitation of bosons. So exactly how the transition happened till now is still like up to debate. So in addition to the specific half-filling case, when you start to dope electrons into this Mott insulator, or the electron also feel the strong interactions. As a result, they can behave very differently, for example, in the form of high-temperature superconductor. So up to now, this is still a very active research in condensed matter physics, how to fully describe or understand these strongly correlated materials. So if we think about the Mott insulator and describe it a little bit more mathematically, what it says is you have very strong correlation. When the Coulomb energy, U, becomes comparable or larger than the bandwidth energy of the electrons. And when you write it in the formula, we know the Coulomb potential is roughly defined as E squared over the electron separation, which is characterized by the lattice size L and modified by dielectric constant epsilon. And the bandwidth, as I mentioned, or it has the upper limit of the kinetic energy at the band edge, which scales as this form, h bar squared pi squared over 2ml squared. So the ratio between Coulomb potential and the bandwidth simply is proportional to electron mass multiplied by the length. So what this tells us is if you can create a larger and larger lattice size L, you always get a strong correlated system, as Mott predicted. If we put in the numbers, we can ask, oh, how large a lattice size you need. So if you have electron mass that's 1 of rest mass of electron, you need a lattice size about 1 nanometer. When we assume dielectric constant of 4, which is dielectric constant of boron nitride. And if you have an effective mass of 0.1, then you need a lattice size about 10 nanometer. So as you can see, this argument is actually rather simple. It's just considering the potential energy versus effectively kinetic energy. And this argument is very general and has been discovered at different time in different systems. And another very important example of using the same argument is a strong correlation of 2D electron gas when there is no underlying lattice at all. So Wigner basically says, if you don't have underlying lattice, this is still a characteristic length scale, and that is electron-electron separation determined by the density. And he basically used exactly the same argument. Or the energy of Coulomb potential scales with 1 over L, and the kinetic energy scales with 1 over L squared. So when you have large enough L, Coulomb potential again will dominate and give you a strong correlation. And the electron will automatically form a crystal, known as a Wigner crystal. However, if you compare the Mott criteria and the Wigner crystal criteria together, you see there's a small quantitative difference. So in order to get a Wigner crystal, where you don't have an underlying lattice, you need the Coulomb potential to be roughly 8 times larger of the kinetic energy if you define this way. A very common parameter people use in the literature is known as RS, which is defined as electron separation divided by 2 times of effective Bohr radius. So it's related to U over K. And in that case, that number has to be larger than 35. So these two are equivalent. So what you can see is in order to get a strong correlation with a lattice like a Mott, you need U over K larger than 1. If you want to push it further, and you get U over K larger than 8, so that means if a lattice is 8 times larger, or density is like 60 times smaller, then you can even get a Wigner crystal. And the reason Wigner crystal is harder to get, at least for experimentalists, the hand-waving way to argue is a continuous symmetry. So it's a little bit harder to break compared with the one with lattice. Okay, so now we have seen that the correlated physics can be interesting, and Mott has an interesting proposal of how to achieve it. So the question is, can we actually make use of Van der Waals heterostructure to make that Gedanken experiment into a reality? And the answer is yes. If you play with 2D material, very soon people realize there's an interesting phenomenon known as Moire superlattice. So the idea is if you stack 2 layered material together, or depending on the atomic registration between them, so this case is graphene and boron nitride, they all have hexagonal lattice. And when you put them together, because their lattice is a little bit different, so the registry between the atom change over distance. And that change gives rise to a longer period lattice. And this is known as Moire superlattice. And when you have graphene and boron nitride, for example, at 0 twist angle, you can get a lattice about 15 nanometer. So that's pretty long. And if you use Mott's criteria, you can easily get strong correlation. So this actually provides a pretty general way to engineer correlation model system in 2D material. So I will tell you 2 specific examples that we have explored quite a bit. One is using transition metal dichalcogenide. You can get a lattice in the order of 10 nanometer, and you have an effective mass of 0.5. So it's very strongly correlated. And I will also give you an example where you actually have a graphene boron nitride heterostructure where you can control a lot of relevant parameters, including band topology and bandwidth in situ with the electric field. So let me just, also this is kind of overall a few things I would like to talk about. I would like to show you that in transition metal dichalcogenide, such as WS2, WSE2 heterostructure, we can realize Mott insulator but also generalized Wigner crystal. And I will also show how does it compare with a conventional Wigner crystal in the 2D limit. And then I will tell you about the ABC trilayer graphene, where you can actually tune a lot of parameters in situ. So let me start with the WSE2WS2 Moire heterostructure. So these two materials has a lattice constant mismatch about 4%. So when you stack them together, even when they are perfectly aligned, they have a kind of a Moire period about 8 nanometer. And or structurally, we can indeed see the Moire period using a high resolution TEM, where you can see the, at least this periodical kind of atomic structure. And if we do STM on this sample, we find this this atomic structure is really providing an effective potential for electrons. So the electron wave function are not homogeneous anymore. They are rather localized at a specific point. So with this Moire period and the large period electrical potential, we should expect strong correlations. And it took us quite some time trying to put contact to the system and see whether we can see indeed a Mott insulator when you have one electron per lattice site. But it didn't work very well because for us it's extremely difficult to make a good electrical contact to the TMD. So as a result, the transport is always dominated by contact rather than what's going on in the TMD material. So we thought it very hard and used the optics tricks that Tony told us. So we came up with a new idea, use optical detection to measure the electrical transport behavior. And the idea is like this. So this, we have 2 layers of transition metal dichalcogenide, Moire superlattice, and we have both a top and bottom gate. So the contact in the system is very bad, so it's hard to do transport, but it's still fine for us to just gate the material and change the carrier density. So once we can vary the density and we have this kind of a partial top gate, what we can do is apply AC voltage to the top gate. So as a result, you can see because of capacitance coupling, the electrons in the 2D material will move around to respond to this gate voltage. And optically, we can actually measure what's the local electron density through its effect on the optical absorption. So what we can do is measure the density change at this point, respond to our AC gate voltage. And the magnitude of this change tells us how many electron has moved. So that tells us about the capacitor. And the speed of this change tells us how fast it is responding. So it actually tells us the RC constant of the circuit. So combining these two, we can determine all the resistance and capacitance using pure optical detection. And that works quite well. So we are able to measure the effective resistance as a function of carrier doping. And we see that it shows a very non-monotonic behavior. So when you add the electrons, the resistance first decreases, then it shows some very strong resistance peaks. The strongest peak that we see corresponds to density of 1 hole per Moire lattice site. So that's exactly 1 hole per period. So that's what Mott tells us. This is a Mott insulator. But we also notice 2 smaller peaks at partial filling of the system. And it happens exactly at like 1/3 and 2/3 filling. Initially, it came as a complete surprise when we observed it experimentally. But once we see it, it's fairly easy to come up with a potential explanation. So this may be the so-called generalized Wigner crystal state. In the case, the Coulomb interaction is long range. Since in this system, the interaction is so strong, it will prevent 2 electrons sit in the same Moire lattice. But it also wants to prevent adjacent electron occupation. So if you avoid all the adjacent site, basically you get the 1/3 generalized Wigner crystal state. And if you avoid only like half of that, you get the 2/3 state. So this tells us actually the interaction in the system is really strong, and the long-range interaction is important. However, people always ask, oh, how do you know it's real 1/3 and 2/3 state? I mean, is it possible they are coming from something else? And it really drives us to ask, oh, can we really solve this problem permanently and image this generalized Wigner crystal directly? And in order to image that, there are several criteria. Or you need to be able to have single charge sensitivity. You need to have nanometer spatial resolution. And most importantly, you need not perturb the system too much to destroy your Wigner crystal while you probe it. So as a result, conventional STM doesn't work. The conventional STM has good enough sensitivity and spatial resolution, but when you bring a tip and try to do tunneling measurement, you destroy this delicate Wigner crystal. So we came up with a kind of a modified technique where we combine the STM with the flexibility of engineering Van der Waals heterostructures. So we actually create a system shown over here. So in addition to this WS2, WSE2 Moire superlattice, we add a very thin BN, a few nanometer thick, and put another monolayer graphene on top of it. So the top monolayer graphene acts as our sensing layer. So where the STM actually tunnel into graphene, so it doesn't disturb the Moire superlattice strongly. And to understand this, at least in a somewhat hand-waving way, we can imagine like this. So if there is an electron lattice, or coming from, say, generalized Wigner crystal, sitting in the Moire heterostructure, the electrons, the periodical electron lattice will change the potential in this monolayer graphene. And when you do STM imaging of the graphene, you will see basically a periodical structure that maps the underlying electron lattice. And this scheme actually works quite well. So here I show you some images of this generalized Wigner crystal. So on the left-hand side, this is a topography image where you can see the Moire superlattice directly. And the red dot illustrates a specific AB stacking site where electrons prefer to sit in. And then when we add the electron into the system, if we add, or say, 2/3 filling, so we get an image like here. So all the bright region is where the electron sits at, and the black region is where you don't have electron. So if we just note all the bright region with this filled red dot, you can see they form a lattice and they avoid 1/3 of the possible site. And when we change the density to 1/3, you can see basically, again, you have indeed 1/3 filled generalized Wigner crystal state where all the nearby sites are empty. We can also see a state at 1/2 filling. So in this case, they actually spontaneously form a stripe phase. So it breaks the total rotational symmetry in the system. Okay. So now we can see that the Van der Waals heterostructure not only allows us to engineer strong correlation, but also give us new ways to probe some interesting phase. And in particular, in this case, allow us to measure some very delicate phases. So a question that we ask next is, can this be good enough to measure the original Wigner crystal where you don't have a Moire superlattice? Let's say we build a heterostructure, swap out the Moire superlattice, I just put a monolayer transition metal dichalcogenide. In this case, we'll have a real 2D electron gas sitting in the monolayer TMD, and we can see whether a Wigner crystal will indeed emerge at low density. So this is some recent picture of electron that we can see. On the left-hand side is when the electron density is very low. You can see there's roughly a lattice over there. So these are basically pinned by disorder. So even if they are not a perfect Wigner lattice, is definitely a Wigner crystal. The electron actually sit at a specific position for hours. So they form really a solid. And when you change the density of the electron, so when you go from left to the right, so you can see this, the Wigner crystal indeed have higher and higher density, but they still remains as a solid. up to electron separation in the order of 20 nanometer. So over here, so the RS value is around 30. So you can see the kind of discreteness is becoming weaker. And when you increase the density further, it changes from a crystal phase into a Fermi liquid phase, and you see homogeneous distribution of charge. And or to show this more carefully, we can actually, let me see, we can okay, we can actually put it in a video, so maybe you can see the evolution more clearly. So at low density, basically, you have small lattice, and small densities. And when you increase the density, basically, you can see that the evolution of Wigner crystal, and until at high enough density, it starts to melt. Okay, so that's all I want to say about the transition metal dichalcogenide. So next we would like to talk about the Moire superlattice you can form with ABC trilayer graphene on boron nitride. So in order to do that, let me first introduce you to the trilayer graphene. Like when you exfoliate graphite, sometimes you get monolayer, sometimes you get bilayer, sometimes you get trilayer. And for trilayer, there are two natural stacking orders known as ABA and ABC stacking. So we'll focus on the ABC stacking. So for each monolayer graphene, you have a hexagonal lattice. You have A and B, two atoms in a unit cell. And in ABC stacking, this AB atom form a stair kind of structure. So in this case, what you can see is some of the atoms sit directly above and below each other. So they strongly hybridize and form bonding and anti-bonding state. So they are pushed away to high energy. So at low energy, we are left with a top B atom and bottom A atom. They have all the same energy, so you actually have a zero gap. They couple very weakly with each other because it needs to go through many steps. So it has a small dispersion, so that means a relatively large effective mass. So unlike monolayer graphene, which is known as massless Dirac electron, so trilayer graphene has a reasonably large mass. It can also have a tunable band gap because, or in a pristine sample, you have zero band gap because inversion symmetry. So the top A atom and the bottom B atom are the same. By applying a vertical electric field, you break that symmetry because these two atoms now have different potential, and you can create a finite band gap. So now if you combine this trilayer graphene with boron nitride to form a Moire superlattice, all these effects still exist, but now you need to add this kind of or smaller Brillouin zone. So what you find is first you develop this rather narrow Moire band. So when you don't apply any electric field, so that's the middle plot, you have zero band gap. So if you apply, say, a positive electric field, you can open a band gap over here. So what you see is when the band gap opens, you effectively are squeezing the valence band, let's say this red band. So you basically are changing the bandwidth, and as a result, you change the correlation in the system. At the same time, you can create a band gap with both positive field and negative field. So if you go through it with positive field, zero field, and negative field, you can see you have a finite band gap, close it, and open it again. And that is a band inversion type of process, where on the two sides, you always have a change of band topology. So yeah, one way to think of it is think about a geometrical topology, where if you have a strip and you kind of change the distance between the top and bottom ribbon at one point and cross it, you can change from a regular ribbon into a Mobius strip. So in this case, so the prediction is we can actually in situ control the bandwidth, so control the correlation and control the band topology. So that could be quite interesting. So we went to make this type of samples with ABC trilayer graphene aligned with boron nitride. And we also make a so-called dual gate device where we have both a top gate and a bottom gate. So in that case, we have two control that will allow us to control the electrical field and the carrier doping independently. So here we show the kind of overall phase diagram where you measure resistance as a function of top and bottom gate. So in this case, if you look at the 45-degree direction, so you are changing the carrier density without changing the electric field. And if you look at 135 direction, you are changing the effective field with fixed carrier density.
Little problem with the sound. I'm going to put this as a microphone. Just keep going.
Oh. According to the theory, so with positive electric field, we'll have kind of a flat band, but is more like a common flat band, a trivial flat band. And on the other side, we'll have a topological flat band. So we can see, in this kind of a phase diagram, what happens. So let's first just look at the transport on the trivial flat band side. If we do a line cut at the 0 vertical electric field, but vary the doping, and this is what the transport look like. So you see some resistance peak, and those one of the peak corresponds to charge neutral point in the system. And the other peak corresponds to completely fill the a band, which corresponds to 4-hole per lattice side, because in graphene you have both a spin and valley degree of freedom. So now if we increase the vertical electric field, we are effectively squeeze the band and increase the correlation. And we can see transport change very dramatically. You start to see well-defined resistance peak at 1-hole per lattice side and the 2-hole per lattice side. And in particular, 1-hole per lattice side is a canonical like a configuration of a Mott insulator. So what you can see, you can actually continuously have a metal insulator transition when you go along the direction of finite electric field. And once the bandwidth is narrow enough, you can have reliable like Mott insulators. So a question then to be asked is, if you have a Mott insulator, is it possible to dope it and realize superconductivity? And to answer that question, we all collaborated together with Professor Gordon here. So we actually searched the phase diagram, and we found that doped Mott insulator don't always give you superconductivity. So we need to look carefully, and in a relatively narrow phase range pointing over here, we actually see the signature of superconductivity, where the resistance has dropped more than order of magnitude at low temperature, and it also shows like a critical behavior where the resistance also becomes higher at large current. Also, it gets suppressed by both in-plane and vertical magnetic field. So we can also map out the kind of a region where we see signatures of superconductivity, and we found it really clustered around the Mott insulator at n equal to n0. And it's reminiscent of what's seen in high temperature superconductor. Of course, we still don't understand the origin, so it requires a lot of more theoretical and experimental work to really understand it. So after we look at this trivial band, we can ask, what happens when you have a topological side? So that means we look at negative electric field. So one thing that I need to remind you is, with graphene, there are always two valleys. So when I say Moire miniband is topological, actually there are two copies of them, one at k and one at k prime. Because they are time reversal pair of each other, they have exactly opposite Chern numbers. So if you have a charge neutral system, for example, the total Chern number equal to 0. So, or if you start to say dope hole in the system, you can see the holes can sit in both bands. And if they are equally distributed in these two bands, it's not that interesting. However, because these bands are not only topological, but also very flat. So you can imagine when you dope the hole to the system, it's possible that you can break the symmetry due to strong correlation. And for example, all the holes go to one valley, and you then will have a magnetic state, but also is a topological chain insulator state. And luckily that indeed happened in real system. Again, working together with Professor Gordon, we were able to show that when you put one hole per lattice side, So the system actually automatically develop a magnetic hysteresis. So that means, indeed, it breaks time reversal symmetry, and all the holes actually prefer to go to one valley. So this type of magnetism is fairly different from the conventional magnetic material we usually see, which is dominated by spin. So in this case, spin plays a very little role. So it's dominated by kind of orbital motion of the electron in the system. And if you look at the quantum Hall signal, you find that is actually quantized quite well at nu equal to 2 state. So that tells us is actually a chain insulator with a Chern number equal to 2. Well, and again, we can also see the signature of the same behavior in the magnetotransport plot, where you basically measure the RXX signal as a function of doping in x-axis and as a function of magnetic field on the y-axis. So in a single particle system like a graphene, you actually see many Landau fans. So in this case, because the strong correlation, it actually suppresses most of the quantum oscillation in the system. So we don't see those single kind of individual electron Landau fans. Instead, you see a very dominating dispersing line here that has basically 0 RXX, so it's like a quantum Hall state, but it's not single particles. Quantum Hall state is like a kind of correlated chain insulator state, and the slope again tells us the quantum Hall number is equal to 2. Okay, with that, I would like to just conclude. I hope I have shown you that already by borrowing Mott's idea, there is actually a very general way to engineer strong correlation in Van der Waals heterostructures. Just by making Moire superlattices, you can have larger period. Naturally, that tend to give you stronger correlation. Although I talked about 2 systems, like a transition metal dichalcogenide and trilayer graphene, this should be applicable to almost any 2D semiconductors. So there are many different systems one can play with. This, to some extent, contrasts to the magic angle twisted bilayer graphene, which you require a pretty subtle effect. So you need a specific magic angle. So like this, by using large Moire superlattice, there is really no magic. You can use it in almost any material. And in the case of transition metal dichalcogenide, we can make Mott insulator generalized Wigner crystal. And for trilayer graphene, it has tremendous tunability. And you can realize basically Mott insulator, superconductor, magnetism, and chain insulator all in the same device by applying electric field. So this will be a really nice model system to study how the different phases get stabilized, how they compete with each other, and how the phase transition happen between different states. With that, I would like to acknowledge people who really did the work. So the graphene work is pioneered, spearheaded by Chern, a postdoc. And then the ODRC signal measurement in TMD is done by Emma and Danqing, and then the STM work is done by Hongyuan and Shaowei. And we have a very strong collaboration with Professor Kromi, Zetto, and Louis at Berkeley, but also for the graphene work, we have a lot of collaboration with Professor Yuanbo Zhang in Fudan University, and also with Professor Golden here. And we have a lot of theoretical support from different theories. And with that, I would like to thank you for your attention and answer any questions.
Okay, questions, please? Yeah, otherwise, the former thesis advisor will have to ask something.
So Feng, you mentioned that the TMD system has robustness that might not be present, for example, in the twisted bilayer graphene, because we can twist to a wider range of angles. Do you know how stiff this Moire is? So if it's at 0 angle or if it's a finite angle, how much the variations in the the twist angle are as you move around?
Are you talking about the homogeneity or like?
Yes, the homogeneity, since that seems to be in the twisted bilayer graphene, something that's a limitation.
I see. Oh, that's a very good question. We don't have very quantitative. I mean, we have some STM measurement. They show the period is actually rather stable, but we don't have huge statistics. So the thing is, like, you already have say a Moire superlattice of 8 nanometers. So even if you have a variation of angle of 0.1 degree, it's going to have very minimal effect on the overall period.
Thanks very much.
Yes.
I have a quick question about the Mott insulator argument. So are there more signatures you look for with other than half-filled insulating behavior? And is it usually I thought you have some kind of magnetic associated to put one, like 1%.
Yeah, so the question is for the Mott insulator, whether there are interesting magnetic orders. And indeed, that's actually one of the open and most exciting direction about this Mott insulator. In principle, like especially for triangle lattice, there are actually theory prediction. They are not only anti-ferromagnetism, they actually can be candidate of spin liquid. So however, experimental probe of those are somewhat tricky. So we are still thinking about what will be the best way to determine the magnetic orders. So a ferromagnetic order is easy to see. But unfortunately, that's not the magnetic state that we see in most materials. For antiferromagnetic state or spin liquid, it requires much more delicate measurement. And we are trying, I mean, both us and the other groups are really trying to see how you can characterize them through electrical transport or optical spectroscopy.
DX?
On the superconductivity phase diagram, are you sure the middle is not insulated?
Are you sure the middle is, oh, okay. Yeah, so in this case, because like David said, there are some intrinsic inhomogeneity in the system. So what we can see is at relatively high temperature, they behave really like an insulator. But at a very low temperature, it seems they are becoming kind of conducting or superconducting. We think it might be just there are some kind of inhomogeneity in the system, so you have a broadening in the phase diagram. But it's a very good question. So if we have really high quality sample, what happens all the way? So that's the future measurement need to address.
Question from somebody who's really competent about these things. How easy it is to position those things? And how large are the domains in which the lattice is coherent, sort of?
Okay, so that's a very good question, and it's one of the...
Seems like black magic.
So, I mean, mechanically, to control the angle, if you just use a good stage, that can be, say, much better than 0.1 degree that you can control. But the tricky thing is actually when you stack them, whether your designed angle will remain exactly as it is. And the answer is very often it does not stick to the angle that you actually use. So it takes a lot of people trying to improve it to make it more reliable of angle control if you want to a specific angle. But however, if you want to make use of the lattice mismatch and just want to have a zero twist angle, that's overall easier. So one thing is the zero twist angle tend to be energetically favorable. So there's some incentive for them to want to be zero twist angle. But the other thing is that if you make use of a lattice mismatch, then the Moire superlattice is determined by the lattice mismatch itself. So a small angle variation don't have too big an effect. So for like how big the domain can be, like so typical sample size are of a few micron to tens of micron people can actually make with reasonable homogeneity of the Moire superlattices.
So Feng Feng, may I ask you, that you worked your way down to an extremely simple thing at one point, which was no Moire, just looking at the intrinsic formation of Wigner crystals. And you know, if I look in the history, the new thing seems to be looking with an STM and you know, this non-perturbative mode through graphene. But you know, what does that tell you about the likelihood of Wigner crystals existing in typical bulk crystals? Because the argument is really not that different. I mean, it depends on the dielectric screening and the mass, but it doesn't seem fundamentally very different.
Yes, in a 3D system,
Right.
not a 2D system. And Wigner's prediction is not confined to 2D system. In 3D system, you should also form Wigner crystal, but you actually need an even larger electron-electron separation. The theoretical prediction is it should be like more than 100 RS. So the main difficulty is like how to make a crystal that's clean enough where defect density is much smaller than the electron density you put in the system. And then also like how to probe it experimentally. With 2D system, the good thing is actually you can use a scanning probe to see them pretty well. A 3D system is actually harder to see the lattice.
But that gets to the second point. So, I mean, clearly there's some role of inhomogeneity because your image is fixed, right? If we're a totally ideal system, it would probably be mobile, basically, to some degree. So how do you preclude the possibility that you're just sort of selectively illuminating different defect sites? Obviously, there's some kind of electrostatic interaction, but what gives you confidence it's not still dominated by intrinsic potential variations and defects?
Yeah, so that's a very good question. Like, how do we know these are real Wigner crystal rather than just potential variation determined by the defect potentials? So one thing is the defect is very important. If you don't have defect to pin the Wigner crystal, you will not be able to see them with STM. But the thing is the defect potential tend to be rather kind of fixed. So the main kind of signature is the continuous evolution with doping. So you can see the lattice actually varies and moves around when you change the doping. So that is a pretty strong signature. These are real Wigner crystal rather than some underlying potential variation. In that case, you'll see the electron tend to be preferably sitting at one point.
Follow up on this question. What I saw in this slide showing the Wigner crystal, you see a resistivity change from 10 to the 8 to 10 to the 9. It's a decade change. Does that number get bigger if you go to a smaller sample that's inhomogeneous? Is that the maximum you see?
Oh, sorry, which slide are you referring to?
If you can go back, you can see it.
Oh, you are saying the resistivity or?
Yeah, resistivity.
Yeah, so that is, so you can see in that case, the overall resistance is very high. So we actually never, so it seems in this case like they never really get, at least in this sample, maybe the defect actually may dominate in some of the transport. So they never get a real metallic state. But what you can see is at least at Mott insulator, the resistance shoot up dramatically. So there's a very dramatic change in the resistance.
No, I was more asking if you make the change of sample size following what Tony's question regarding defect size and homogeneity, then you would see that to be different. What kind of variation? Not how big, what's the biggest change of resistance as you go into the
Yeah, so okay, so there are two so-called Wigner crystals. So this is so-called the generalized Wigner crystal where you have underlying lattice. So in this case, we do see a large variation when you go from sample to sample. So I think what Tony was referring to is more like this one, the intrinsic Wigner crystal, where you don't have Moire superlattice at all. And you just look at where the electrons sit, you'll find they have no preferred position where the electron want to sit. So that tells us they are really not determined by a defect potential.
All right, maybe time for one last question. How about one from the students? are. Yes, please.
Okay, I have a question about this slide, actually. You played a little video where we're moving between...
Yeah, that's the next one.
What are we qualitatively supposed to notice about this pattern as the densities change?
Oh, sorry, I went too far. So basically, the pattern, what you are supposed to see is at low density, electron and the electron are well separated. And you basically see bright spot and dark area. So that means the electron actually are more or less fixed. They are like a crystal. They sit at specific position and don't move around. And when you increase the density, this crystal, or since there is no defined separation of electron, when you increase the density, what you can see, the separation between electrons becomes smaller and smaller. So you basically have a denser crystal when you compress it. But when you compress it too much, or it doesn't want to stay in the crystal state, it actually becomes a Fermi liquid. So when you have a liquid, the electron moves around all the time. You don't have a variation of electron density, and you basically see more or less a homogeneous distributions. So that's what this should be. And the movie is basically just connecting all these pictures together.
Thank you.
Last question?
Yeah, thank you. You try to achieve Mott insulator by changing the L versus, do you think it's possible to do it through straining, actually stretching?
Yeah, so you can actually, to strain and vary L, you can only have a few percent change. But however, strain actually can modify the band structure quite dramatically. So if you apply strain, again, you can vary the competition between U and W if they are already fairly close. So then you can vary their competition and realize different state.
Well, let's thank Feng Wang for a wonderful talk.